Welcome to this latest training video from the Focus Training Group, where we're looking at Level 3 electrical design and cable selection. Today we're going to take a look at voltage drop. This is video number 6 in the basic circuit design series, so if you haven't already done so, please subscribe to our channel, and that will help you view the initial 5 videos leading up to this point. Once we've selected our circuit conductor size from applying rating factors to either IB or IN, depending on whether overload protection is required or not, we must see if the requirements for permissible volt drop are met. Voltage drop is a very important consideration because if our supply voltage drops too low, this could affect the operation of protected devices and the operational characteristics of some of our installed equipment. Permissible volt drop limits are found within BS 7671 Appendix 4, and the percentage volt drop permitted for public and private supplies is shown in Table 4AB, a copy of which is shown on the slide here. This is broken into 2 separate supply types, one public low voltage distribution system and one private LV supply. Today we're just going to focus on public low voltage distribution systems. However, if your workplace scenario or your exam questions etc. are based on private supplies, you would have to use the percentage limit shown for that type of supply. So we can see for public low voltage distribution systems, the permissible voltage drop limit for lighting is 3%, and for other uses, sometimes referred to as power, is 5%. We can see on the left hand side how this would work for a 230 volt single phase system. The first calculation shows us the 3% limit for lighting circuits, which would be 6.9 volts, and a 5% for other uses, which would be 11.5 volts. Over on the right hand side it shows us these limits for a 400 volt 3-phase supply. We can see that 3% of this would be 12 volts for lighting and 5% for other uses would be 20 volts. To be able to perform the voltage drop calculation, we need some volt drop values, and they are given to us in the applicable tables of BS 7671 Appendix 4. From the last video looking at how we size our circuit conductor, you may recognise some of these tables, as they usually come in pairs. The first one would be to show the current carrying capacity of the conductors, and then the partner table would show the voltage drop for each conductor. The table we have an example of on the right hand side is table 4D1B, and this is the partner table for table 4D1A, which is single core 70 degree thermoplastic insulated cables, non-armoured with or without sheath. The first part of this table, 4D1A, would show the current carrying capacity of the different size conductors depending on reference method and type of current. Usually underneath these tables, or perhaps overleaf in your regs books, would be the partner table. So in this circumstance it would be table 4D1B, which shows voltage drop per amp per meter for the same type of single core 70 degree thermoplastic insulated cables. We can see we have the conductor sizes in millimeters squared down the left hand column, and then we have separate columns depending on the reference methods and the type of current. The numbers shown in each column and corresponding with the circuit conductor size are the voltage drop per amp per meter, and this is given in millivolts. So for example, if we look at 2 cables single phase AC in reference methods A and B, for a 1.5mm squared conductor, the millivolts per amp per meter value would be 29. The formula we need for our voltage drop calculation is shown on the left, and this is VD, or voltage drop, will be equal to our millivolts per amp per meter value taken from the appropriate table, times by IB, which is our design current, times by our length, which will be the measurement of our circuit in meters. We then need to divide this top line by 1000, as our volt drop values from the relevant tables are given in millivolts, and we require our final answer for voltage drop to be in volts. So let's have a look at an example. We've decided that a 2.5mm flat PVC 70 degree cable is suitable for installing a supply to a fixed panel heater. The design current is 5 amps and the run is 45 meters, the supply voltage being 230 volts single phase. Our first requirement is to look for the relevant table in BS 7671 that will give us the voltage drop values for this type of conductor. In this case we would be choosing table 4D5, which is for 70 degree thermoplastic insulated and sheathed flat cable with protective conductor. This table slightly differs from the others because it shows the current carrying capacities as normal, and then it has a separate column over on the right hand side for the voltage drop values. So first of all, we have to take the information from our scenario and look for the millivolts per amp per meter value. If we look down the far left column down to 2.5 mil for the size of our conductor, and then follow that across all the way to the far right column, we can see our MVAM value is 18. The other bits of information we need from our scenario is IB, which is 5 amps, and our length, which is 45 meters. We put all these figures into our formula, and we have voltage drop will be equal to 18 times 5 times 45 divided by 1000. We have then redrawn that formula, which shows the product of 18 times 5 times 45, which is 4050, and divide that by 1000. This will give us our total volt drop of 4.05 volts. Once we have calculated this volt drop for our circuit, we simply have to compare this with our maximum figure that is permitted for our supply and circuit type. Provided we've selected the appropriate size cable, the volt drop will be within permitted limits. If we cannot achieve a volt drop within these permitted limits, we will have to go back and select a larger cable size and repeat the volt drop equation again until it complies with the requirements shown in BS 7671. So in this circumstance, we were talking about a supply to a fixed heater, so that would come under other uses. And from our calculations earlier on, we discovered that this 5% in a 230 volt single phase circuit would be 11.5 volts. We then look at the outcome of our calculated volt drop, which is 4.05 volts. Therefore, our voltage drop is well within the permitted limits. Remember, if we couldn't achieve these permitted values, it's because the length of our conductor offered too much resistance. We then get around this by selecting a larger CSA of conductor because, as I'm sure we'll all remember, increasing the CSA of a conductor will decrease that resistance, and therefore will hopefully bring our voltage drop back within permitted limits. We hope you have enjoyed this video. Please subscribe to keep up to date with this circuit design series and other relevant content that will be posted. Next up, we're going to look at how we calculate our earth fault loop impedance, otherwise known as ZS. See you soon.